Many people think an air conditioner blows cold air out of thin air, but it's really just a porter of heat. The refrigeration principle of the world's first air conditioner is so simple you won't believe it. Take a sealed cylinder and push down a piston to compress the air. The piston moves against the molecules and the temperature rises sharply. In turn, loosen the piston. The high-pressure air pushes it back and the temperature drops. Using this principle, take a hand cylinder, turn the flywheel, and press down. The air inside is forced to compress and the temperature soars. Next, wind the pipe into a spiral and soak it in cold water. When the hot gas passes through the coil, the heat is forced away by the water, turning it into a high-pressure gas at room temperature. Finally, convey this room temperature gas to another expansion cylinder. With the instant release of space, the gas expands violently, and the working temperature of the piston plummets again. This is the physical journey of the first air conditioner. But making loops with regular air is too inefficient. To maximize heat absorption, engineers replaced air with what we often call Freon. Its boiling point is ridiculously low. For example, R32 refrigerant, commonly used in air conditioners today, will boil and vaporize at anything above -60 degrees Fahrenheit. Just put pressure on it and it's forced back into a liquid state. Now let's put this refrigerant in a home air conditioner. Let it circulate through the system and see what happens. Take a look at the major components. The outdoor unit features an axial fan to exhaust heat, a compressor and a condenser made of gray fins and copper pipes. The indoor unit mainly has three components: the evaporator responsible for absorbing heat, the expansion valve to control depressurization and cooling, and a blower fan that circulates cold air into the room. First, the refrigerant goes down the pipe into the compressor. Under intense pressure, the volume of the gas shrinks instantly, and the temperature shoots up to 160 to 180 degrees Fahrenheit, turning into a high-temperature, high-pressure gas. Obviously, this hot gas can't be sent into the house. It must be forced to reject heat first. So, this gas is pressed into the condenser ahead. The condenser is made of copper tubes that conduct heat extremely fast. As the hot gas travels inside the long coil, heat transfers to the surface of the copper tubes. At the same time, the outdoor axial fan blows across the coil, forcing the heat off the tube walls and into the outdoor air. After this wave of physical air cooling, the refrigerant temperature drops from 180 degrees down to about 120 degrees Fahrenheit. Next, this 120-degree liquid refrigerant flows down the pipe straight into the indoor unit's expansion valve. To put it bluntly, the expansion valve forces the fluid through a narrow slit, and the size of this gap automatically adjusts based on thermal expansion and contraction. When this high-pressure liquid squeezes through the tiny opening, the pipeline space ahead suddenly opens up, instantly releasing the pressure. As the pressure plummets, the liquid refrigerant starts vaporizing immediately, and the temperature drops again, plunging from 120 degrees to a 40 to 45 degree gas-liquid mixture. It then rushes into the neighboring evaporator coil. At the same time, the indoor blower fan spins at high speed, forcing hot air from the room through the dense, freezing fins. The moment the room air touches the ultra-cold copper pipes, its heat is instantly sucked up by the refrigerant. The air, losing its heat, cools down completely and is blown back into the room by the spinning fan. That's how you get that crisp, cold breeze. Additionally, by opening and closing, the expansion valve precisely controls the refrigerant flow. After the refrigerant absorbs the indoor heat, it becomes a room temperature gas of about 85 degrees Fahrenheit and is pumped back into the outdoor compressor. Round and round it goes. The heat in your home is moved outside, little by little. There is no cold air created out of thin air, only pure mechanical workmanship.